says 2D superposition of electric forces, and this is the tail of 3 particles, 2 of which were positively charged, the other one was negatively charged. They were put in space like this, and what do you know? This negative one, it felt some forces. We could figure out the direction of those forces just by looking at these 2 other charges. Well, we've got this charge here. Let's label things A, B, and C. Why don't we? A, B, C. Cool. Okay, so because A is here, B is going to get a tug in that direction. Okay. And because C is here, B is also going to get pulled because these are oppositely charged. B is going to get tugged in that direction. So it should make sense that when we let all of these charges go, that B will move in this direction, assuming that A and C are fixed in space. Okay, let's try and do the same thing. I want to know the net force on B. Remember, the net force is crucial, right? Because if we can get the net force, well, we could figure out the acceleration of B as well, because we know Newton's second law by heart. Or hopefully we should know it by heart at this point in the course. Okay, so to do this, we need to understand that the electric force is a vector. Electric force is a vector. So we're going to treat this... Oh, I should have done this in orange. Let's do this in orange. Pretend that's all in orange, okay? We're going to treat this like... we can just move these around because they are vectors, and we're going to figure out the resultant vector. So let's do some tip to tail. I'm going to pull this vector over here and draw it in space. Here we are. There's that vector. And then I'm also going to pull this vector and draw it on top. So something like that. So this is FE1 or FEA because it's from A, and then this is FEC. FEC, FEA. Okay. So let's suppose that these were positioned such that this made, let's say, a 30-degree angle. And let's say we knew all of these charges and we knew the distances so that we could solve for the actual force values. And let's give these some force values. So let's say that this is 12 newtons. We did the calculations out and we found that this was 10 newtons. Okay, so I could plug that in over here. Remember, the resultant vector is this vector. After we do tip to tail, this is the vector that will be the net force. And that makes sense. The negative charge should move in that direction. That should be the direction of the net force. Okay. Well, now that I know this angle, I can break this up like I have practiced so many times in this course. I'm going to break this up into an x component and into a y component. So it's like I'm taking out the overall purple vector because it has a component in x and in y and turning it into both of those components on their own. So when I do 12 sine 30, I get 6. So this pink vector has a value of 6 newtons. And when I do 12 cosine 30, because this angle is 30, I get 10.4. Okay. So this was 12 sine 30, and that was 12 cosine 30. Which leaves me with this side here, which is 10 minus 6. So this must be 4. and that side is 10.5. So let me draw this final triangle. This is the one that I'm after to get net force. I've got this side, 10.4, down by 4 newtons, and my net force looks something like that, F net. I have two sides, and I want this, my hypotenuse, so I can do a little Pythagorean theorem. 4 squared plus 10.4 squared is equal to the net force squared. And I can square root all of that. 4 squared plus 10.4 squared is equal to the net force. And that's great, because now I could figure out maybe the acceleration of this electron, or negative charge. I didn't say it's an electron. Maybe it is. All right. Until next time, I'll see you later.